those who, and there's only about 2 people in the room who do know me, I'm Professor Nicola Morley. I'm from the University of Sheffield, from the Chemical Materials and Biological Engineering Department, and I'm also the Deputy Director of the Network Plus, so I keep hyping in shape normally by answering his questions. So I get to chair this session as well. So hopefully you've had a lovely lunch, and I get to invite our first keynote speaker of the afternoon, Ampea Karikari-Boateng, who is a Principal R&D Engineer for the Offshore Renewable Energy Catapult. So thank you.
Good afternoon, everyone. My name is Ampea. I'm from the R&D Catapult, and I'm very glad to be here to talk to you today about how we're transforming offshore renewable energy with AI, and in particular go into detail about how multimodal AI can also play a part in that. So today I'm going to be talking, maybe introduce myself a little bit and introduce R&D Catapult, who we are, and then I'm going to move on to talk a little bit about some of the AI applications that we've had in offshore renewables. And then I'm going to conclude by just showing some of the potential impact and some of the areas that multimodal AI can have. So, as I said, I'm from R&D Catapult, which is the Offshore Renewable Energy Catapult. That is one of several catapults which have been set up by the UK government, and mainly to support businesses transform ideas from ideas into products and services. So there are loads of different catapults, like digital catapult, cell and gene therapy, medicine discovery, and so on. We focus mainly on offshore renewables, and we have 8 UK regional centres with over 300 engineers and specialists in different sectors, mainly aimed at accelerating offshore renewables. So the key role that we tend to play is we kind of sit between the industry and provide kind of cohesion. So one of the key roles we play is we sit between academia and industry, and we bring loads of great ideas from academia, from universities, into the hands of people in the industry players. And as part of that, we have loads of university partners, some of them shown here. So we have like loads of partnership for de-risking technology. Maybe I could have just shown you my office is at the National Renewable Energy Centre, which is just slightly north of Newcastle. And we have a lot of assets for de-risking offshore renewables. So some of the assets include testing for wind turbine blades, the nacelle as a whole, different robotic devices. And here is one of our test rigs. This one is in Aberdeen for testing cables. I will be introducing a little bit more about this wind turbine here, which is our R&D wind turbine. I'm introducing that because just to give a bit more idea of the scale of wind turbines, and I will also be talking about some of the things that we've done as part of this research on this wind turbine. And just to give an idea of the scale of these wind turbines, they are very large. So for our wind turbine, we've got the nacelle height, which is well over 100 meters. But some of the wind turbine blades that we've tested at our test facility exceed 100 meters. So just one single blade is more than 100 meters. So these are large equipment. So we do a lot of work across different areas. I'm not going to go into too much detail about it, but basically there's a lot of different areas of offshore renewables that we work in. A lot of my work is more focused on smart O&M, and I do a little bit of work across some of these in terms of applying AI for that. Several talks in this morning have made mention of things like digital twins, AI, and their potential transformative impact. And in the offshore renewable industry, we need that AI digital twin to have the big impact because one of the UK's goals in trying to achieve net zero is that we aim to have 50 gigawatts of offshore wind by 2030. So far, we're sitting about, as of late last year, we were sitting about 15 gigawatts. So that's 15 gigawatts accumulated over the last maybe 20 or so years, and we're trying to get up to 50 gigawatts in the next 5 years. So that is a very challenging ask, and we need digital technologies to come in and play quite important role in helping accelerate that. And AI plays a fantastic role in different stages of the development of wind turbines. So I am using wind turbines and offshore renewable energy kind of synonymously. We work across offshore wind, wave, and tidal, but offshore wind industry is a lot more advanced, so I'm mainly going to be focusing on offshore wind. And when you're talking about things like selecting which site you want to install wind turbines, you want to have a wind farm, AI plays different roles in some of the resource assessment, plays roles in assessing or optimizing some of the layout for a potential farm. It plays a key role in planning and development in terms of analyzing data that you may take from surveys or data that you need for doing your environmental impact assessment. Helps in construction and in installation by helping you optimize your material flow and your supply chain. One of the key areas which I will be talking more about is in the operations and maintenance. So that is one of the key areas that AI has been advanced in the offshore renewable industry, and I will talk about some of the examples showing how AI has been used to help operations and maintenance, and also end-of-life decision-making for decommissioning. So in the next phase, in the next section, I'm mainly going to be talking about how AI is being used for predictive maintenance and talking about several projects. The first one I want to talk about is a project we carried out a couple of years ago on pitch bearing damage analysis. So wind turbines, the wind turbine blade sits on a bearing, and the wind turbine blade needs to be able to pitch, which is like move around, so that it's able to either catch the wind to produce more energy, or maybe not catch the wind to reduce the amount of energy capture. And as I mentioned earlier, these wind turbines are massive. So you're talking about a bearing, but maybe something about 5 meters in diameter, and is designed for an operational life of maybe 20, 25 years. So there is a good need to understand how the bearing is accumulating damage over time. And there are loads of ideas around standards or engineering approaches for assessing how the pitch the pitch bearing is degrading, but often it is very challenging for these engineering models to capture the full kind of operating conditions. So the turbine is subjected to quite a lot of complex loading conditions. So both sort of like radial, axial, and moment loads, and it produces this really complex sort of loading condition on the different rollers. And so it is very difficult to use an engineering approach to monitor this over time. There are some additional challenges here, which is that a lot of the data that we get from wind turbines, a lot of the data, not all, but a lot of it comes in the form of SCADA data. So that's supervisory control and data acquisition system, which is very common in several industries. And these SCADA data often comes in 10-minute intervals. But as you can see here in this chart, within a 10-minute interval, there are loads of different movements. So the top is like the pitch angle, showing how the pitch bearing is angled, is pitching, and the loading, so that's one of the loads. The combination of the different colors form together to influence how much damage there is. But the data that we often get is just like for this window, you probably get one data point. So some of the challenges here is if you want to use an engineering approach, you don't have this level of information available unless you go and heavily instrument your wind turbine, which is very challenging to do, especially if you want to do it for a fleet of wind turbines. So what we do is we harness AI to help us make predictions of what is happening within that 10-minute gap, just using the single point that we get from that 10-minute gap. So we're able to make these. So just to shed a little bit of light, we use a combination of simulations and highly instrumented turbine to just correlate to validate the process to make sure that the AI is making sense in terms of like the predictions. So we use that, and the AI is able to make good predictions of what is happening within that gap. And in addition, what we use this information to do is we use it to feed forward for additional inputs to calculate how much damage is happening over specific periods of time. So with the chart on the left, basically what you can look at is you can look at specific periods where the bearing is accumulating damage at higher rates. You can understand a little bit about some of the operating conditions which influence the damage on the bearing. And on the right, it shows you the sort of accumulation of that damage over time. So you can look at your turbine maybe in 10 years, maybe in 3 years, 20 years, and ask yourself how much damage has it accumulated over time. And all this is only capable through the fact that we're using AI models to fill in the gap where we don't have any data. So another project that we've used AI for is to detect the fault happening in the pitch system. So I talked about the pitch, the pitch bearing, which is a bearing which supports the blade, but it has a system which kind of moves the blade up and down. It contains a lot of different components, but the question is, how do you monitor each of those components? It is very difficult to monitor all the components by installing individual sensors, because the turbine has 3 pitch systems, and you will have to install several sensors. So the question that we were faced as part of this piece of work is, how can you just use the data which already exists as part of the SCADA data, which is the 10-minute average data, to make an indication of the pitch system health condition? And so in a similar approach with this, one of the key things that we did was to use multiple models, but one of the key steps that we needed to do was to understand whether the turbine was operating in different kind of regimes. So one of the key things which helped us make a model which is able to predict the turbine fault was to look at the different operating regimes. So more or less sort of like did a bit of like a clustering, use a clustering approach to help us to detect the operating regimes. And then from that, we're able to understand how to categorize the data set and then use a different model to help us predict the fault condition. When we were carrying out this project, we had loads of challenges. One of the challenges that we had was the fact that we use temperature sensors, and it was extremely difficult to identify the different operating regimes, simply because after interviewing and having loads of different conversations with operating and maintenance technicians, we found out that sometimes they are leaving hatches or doors open, and basically when they left those hatches open, there was like airflow going through the turbine nacelle, so influencing the results or influencing the sensor values that we were getting. The only way we were able to get that insight, that was simply to talk to a lot of people. Some of that information was captured by some of the O&M information, O&M reports, which existed, but it is very difficult to like read through all these O&M reports and then use the data. I think that is one of the potential areas where if we were to carry out this project again, I think trying to use a bit of a multimodal approach, combining some of the textual information from the O&M reports plus the SCADA data, which is tabular in nature, could yield very useful impact in terms of allowing us to carry out this very in a much more timely and much more efficient way. Another project that I want to talk about a little bit is the monitoring of cables. So we're talking about offshore renewables. So offshore renewables, these wind turbines are located offshore, sometimes could be 50, 60, or even 100 kilometers offshore, and you need a cable to transport all that power generated offshore back to land. And these cables, one of the problems that they tend to have is there is degradation in the insulation of the cable. That is one of the most common failure modes. And it's very difficult to detect because these are microscopic water trees which form in the cable insulation. And as you can see, we're talking about micrometer type scale. So one of the things that we've done in terms of investigating some of the causes, some of the water tree formation in these cables is we take little slices, little samples from cables which have these problems, and then we, in the past, basically had a technician who went through under a microscope and had a look and pinpointed whether there were water trees or not. That is not a very efficient way to detect these water trees, so we decided to use more of an AI approach to help us detect some of these water trees. That was quite successful, but there are still a few challenges which often create issues, some issues around the fact that the orientation of the water tree, for example, may not be in one kind of orientation. So the water tree may be rotated at an angle. Sometimes you get a bit of like a high contrast in terms of the image that is captured. Sometimes you get low contrast and the image quality can vary quite significantly. So all this information, these are challenges that we were able to overcome, but in a lot of cases, we overcome these by kind of purely kind of human intervention and human understanding. So it's purely the engineer kind of engineering features, engineering things to make the detection easier. But we think that with the things like multimodal AI, maybe there can be a combination of using some of the images, some of the textual information from reports, or perhaps even some of the data, measurement data, to give a bit more context to some of these detections that we make in that. So another area that I want to comment on is one of the pieces of work that we've done in the past is to look at how can we extract information out of O&M, operation and maintenance reports. So as I mentioned earlier, a lot of the time, a lot of the work that we do tends to look at kind of unimodal models, and a lot of time there's a human being needs to go and read reports, so many different reports, and they have to be able to capture the important things in that report and then feed that through to like the feature generation and feature engineering to make different models. It is very challenging because I give an example of our lever mouth turbine, which is our demonstration turbine. For that single turbine, you get daily reports, you get weekly reports, you get monthly reports. Some of the information is captured in daily reports, others are captured in like weekly or monthly reports. So it's very difficult for a person to go and read like all those reports. That's for one turbine. But when you consider in a scale of a wind turbine of having maybe 50, 100 turbines, it's nearly impossible to necessarily go through, have a look, and read that. So this particular work we initiated to just help us get rid of some of the reading that needs to be done to enable you to develop better AI models. But we see the impact that multimodal AI can just have in terms of maybe creating a shortcut where you can feed both the O&M manuals or O&M reports into a model as part of the creation of a model for condition monitoring. So a lot of this too, we've used the kind of retrieval augmented generation just to generate things like summaries, just to help us have a bit of context, just so that if there's a data scientist looking at how do you create a model, maybe if they see something whilst kind of reviewing the data they can have a quick knowledge bot of the maintenance manuals, and like here, just ask a very quick question. So you can ask just a quick question, get some information back in a way that allows you to follow on. Another way that we've used this model is we've got a lot of scatter data, so that is tabular. So that is tabular data, and so we can also look at how can you interpret that tabular data, helping you to kind of do better data engineering for your model. Once again, that is how we've used it. So in the current state, we haven't used it in a full chain of like a multimodal application, but that is a massive opportunity. That's a thing that we're hoping to do in the future. So just to give a bit of a summary, I've only talked about just a few projects, but there's a lot of condition monitoring tools that we've developed based on AI. All these tools shown here are mainly based on unimodal AI techniques. If we had to go back and redo this, as I've highlighted, we may want to approach that in a very different way, because there's been a lot of work done by the engineers to make sure that they bring context into the data that they are generating to create these models. But in the future, we're hoping to have a bit of a more streamlined, maybe multimodal approach, which allows us to get rid of that, let's say, pre-processing and data engineering stage. Just to give a bit more context of precisely why we use AI. So one of the key reasons why this is very important is because AI allows us to do a lot of analyses that we won't be able to do without AI. So in a lot of cases, we've got scattered data, which doesn't necessarily have the right resolution. Like I was showing earlier, you need to fill in some of the gap. When you have loads of things like high frequency data, there is a lot of processing that you need to do. So it's difficult to make things like automated fault alerts, because you have to churn through a lot of data. But using AI, you can use like lower resolution data and kind of generate very quick automated alerts. You can generate reports. You can have like a flexible reporting, run everything on the cloud, or just have an API interface just to connect. It is a lot difficult if you have to run full-blown simulations every time. So these are some of the areas that AI has helped in the operation of wind farms. So I also wanted to highlight also some of the opportunities that we may have in the near future around using multimodal AI approaches for developing some of these tools for offshore renewable energy. So one of the projects that we are currently undertaking, which we believe we will definitely require some aspect of multimodal AI, is a project called Subsea Soundscape. And what that project is aiming to do is, as part of that project, we are currently installing a lot of sensors around the Celtic Sea. So these are acoustic monitoring sensors, and some of these sensors will be used to monitor like marine mammals. So if they are kind of cetaceans or minke whales or whatever porpoises, they will be kind of detected, and we're hoping to understand the whole landscape of how marine mammals are in there. But that is only the sound. There are so many different aspects which feed into that kind of ecosystem. So this is a map, but there are several maps of this kind of that look like this, which shows things like species density, which may show things like, let's say, plankton density, or maybe different temperatures, different kind of operating conditions. And what we're hoping to do is to get a bit more of a broader understanding of the different factors which influence these mammals, and we can basically create a bit of a model which kind of captures all the influence and impact factors for these marine mammals. The aim of doing this is mainly to understand what the area looks like, because we're planning to put a lot of wind turbines there. So with this, we're able to understand how the wind farms will affect those mammals, and we are also able to understand how we will continuously monitor those populations once those turbines are there. So other things, data sources that we will also collect is eDNA, which is just collected samples. So within all that, you can just see the different types of data sets which will be collected around that same area. Typically, like I mentioned, we have in the past relied on humans to kind of interpret these data from one type of mode into another and create models, but we're hoping this will, we're hoping to potentially create different models. So hoping to use sort of like the bathymetry and the habitat maps to identify the sensitive zones for different species. We are hoping to combine things like some of the turbine specs and noise level to estimate potentially the acoustic footprint that we may have in that region. Also maybe combine things like drone footage and acoustic signals to confirm whether like a species is actually present. So if you detect through the hydrophone a species somewhere, you may send a drone to make sure that you actually can confirm that what the hydrophone is picking up is correct. So that is just highlighting a particular, that's just highlighting a particular application of multimodal AI, but the range of applications for multimodal AI in offshore renewables is absolutely endless. I've just given a couple of examples of how things that are being considered. So in terms of combining some of the inspection images from the turbine blades with the noise to detect how much erosion there is on the blades, because when you get the blade eroding, you get slightly different noise signature. So you can have a bit of a multimodal approach to kind of detecting some of that blade. Similarly, there are kind of combinations of things like thermography and vibration analysis, or like what I've talked about already, the combining some of the measurements with the maintenance records. And the key thing that we aim to obviously achieve is to improve like the data input process. We hope to kind of enhance the fault detection and improve the accuracy as well. And also one of the key elements here is to provide the contextual awareness. So I think that is one of the things which is hugely missing, and all that contextual awareness that we have in our models is provided by humans, as in like an engineer who understands models, who understands maybe O&M records, who can provide that contextual awareness, or who can contextualize what a model is outputting. But in this case, the model can build in that kind of contextual awareness and also helps in generalizing and improving the explainability. So I'm going to end by maybe throwing out a bit of a challenge to everyone. I know there's a lot of people working in the field of multimodal AI, and maybe to highlight that there are loads of potential applications in offshore renewables. One of the biggest applications which will definitely need multimodal AI is in the area of robotics. So currently we use a lot of robotics for inspection and also for surveys. Maybe for repairs, not as much, because it's very challenging at the moment. It's only in the infancy that we're starting to consider robots for repairs, but there is a broad range of different applications where multimodal AI can play a big role in offshore renewables. So that brings me to the end of this talk. So I hope you enjoyed it. I hope you found some of it useful. Thank you very much.
Okay, do we have any quick questions? Right, so at the back, has somebody got a microphone? Yep, thank you.
There we go. Thank you for what an excellent talk. So I'm from a manufacturing hub, which, funnily enough, reflects this a lot. So it's around end-of-life REX, so remanufacture, repair. If we haven't been doing our job, hopefully you've heard of Rescue M, but if not, you do now. And funny enough, we're looking at some of these large structures and what can be done at their end of the life, particularly as it relates to automation and robotics. I wonder if you could possibly touch on that. You've done a lot of condition modeling, remaining useful life estimation. What happens, or what have you seen, I suppose, from this particular sector at the end of its life in terms of recycling, repair, remanufacture? If you could just touch on that, please.
Okay, yeah. So offshore wind turbines are generally designed for about maybe 20, 25 years. And so a lot of the turbines which were put in the water, most of the turbines were put in the water maybe 15, some of them, the oldest, maybe 15 to 18 years. So they're now approaching the end of their lives. So some of that end of life decision is something that is not, the end of life picture is not fully clear, but we're preparing for it in different aspects. So some of it is just purely from an engineering perspective of making end-of-life decisions. So for example, one of the algorithms I showed for the pitch-bearing remaining useful life allows you to assess how much remaining useful life you have, so that you may either do a life extension where you say, okay, the turbine has not use up all its life, so maybe we extend how much we extend, or maybe repair a little bit and extend that, extend the use of a turbine. Alternatively, you can decommission it. And one of the main things when you decide to decommission is you need to look at some of the environmental assessment, and one of the areas which is becoming more and more of a hot topic is the sustainability aspect of what do you actually do with the turbine when you take it off. This is not a very common thing, but let me give an example of, I forget what the wind turbine is, but there was a wind turbine which was located somewhere in the Netherlands, and at the end of the life, they found that it still has a bit of life in it, so they refurbished it and they've put it on a wind farm in Scotland. So technically, in some cases, you can reuse some of those components, but to be able to do that, you need to rely on like useful condition monitoring to be able to do that. And the other aspect is, even if you're not able to do reuse or extend the life, there is also the consideration for things like circular economy. Some of the approaches or some of the things which have been proposed is maybe having something like a digital product passport, which tracks the component throughout its life. And so once again, partly because the industry hasn't gotten to that part in a big way yet, we have loads of plans for what to do when we get there, but there isn't, we're not quite there yet.
No, that's excellent. I think I have to have a chat with you after.
Okay, because that was a very long question and answer, which is fascinating, because digital materials passports is something that I know about as well. Well, I'm going to thank the speaker again because it was, and you can catch coffees in about whenever the coffee break is if you want to speak more and have further questions. So let's thank the speaker again.
Yeah, thank you very much.
And